All right. This is gravitational potential energy. Yes, you learned it 2 units ago, or you relearned it 2 units ago, but remember that gravitational potential energy is different for an orbit, for orbits, particularly because the gravitational force, is a little bit different, right? Okay. Well, we learned that work is the integral of force. Work is also known as the change in kinetic energy, and any change in kinetic energy should be accompanied by an opposite change in potential energy. That's why the negative's there. So we can actually just say that potential energy is equal to the negative integral of force, dot dx. Okay, so to use that last fact, I can figure out the expression for this. The easy derivation for this is that if I know that the gravitational force is equal to negative big G little m big M over r squared, okay, I just need to integrate this, or I take the negative integral of that to get G little m big M over r squared to get dx, to get the potential energy of two objects that are some distance apart from each other, right? Well, all I got to do is actually what I'm going to do is I'm going to rewrite this so it's a little bit easier to take the integral of. I like having everything in the numerator when I take my integrals. You obviously you do your own thing, right? As long as it's right. Okay. This GMM is actually all constant. Even the negative is constant too. So I can factor that out, and the negative and the negative make a positive. So this really becomes potential energy is equal to G little m big M. Okay. Um, and the r would become r to the negative 1. So this is going to be times r to the negative 1, and then this ultimately ends up becoming um, g little m big M over r. Okay, and this is an indefinite integral. So this is an indefinite integral, um, but you don't actually need to have a plus c attached to it. Um, so you don't actually need to have the plus c attached to it, because there would be, I guess, if you had like some initial gravitational potential energy, maybe you could, but pretty much in general, there's not really, you don't really have to consider a plus c. You're really just considering this equation kind of in a vacuum. Um, oh, and I'm so sorry. This actually will become negative again because of the exponent here. So this actually ends up being um, u equals negative g little m big M over r. Okay. So that is actually the form right here. So there should be a negative right there on there because, negative right here too. Okay. Because again, that exponent, when it gets brought down, or when it gets brought back or whatever, then you do have to bring that negative there in front. Okay. Okay. How far must the two objects be if they are to have zero potential energy? Well, we use a very professional physics term to describe this. We say that for the potential energy to be equal to zero, okay, the distance needs to go to infinity. Okay, you might see this represented in multiple different ways. It may say that the spaceship is infinitely far from the planet or whatever, but it will more than likely say this very professional physics term, which is very far away. Okay? So if the problem says the spaceship initially starts very far from the planet, it means that it's infinitely far. Yes, that's not technically proper. I don't think they care, and I don't care. Okay, so just know that they'll probably that if you see very far away, it means infinitely far away. Okay. Potential energy gets more negative. What that means, the wording of this is kind of confusing, but it means it gets more negative. What that means is that the magnitude is getting stronger, but it's keeping the negative sign. Okay. The reason for that is because as objects get closer, okay, they speed up. They speed up and gain kinetic energy. So potential energy must decrease. Okay. so PE gets more negative, okay, because it keeps decreasing. Well, decreasing means it's increasing in the negative direction, right? If you've ever seen, well, you have seen it, but if you remember your equation mgh for gravitational potential energy, that is that equation and this idea that U equals 0 on the ground is actually just a linear approximation of the true gravitational potential energy. Um, you can set any point as U equals 0 as having the 0 point because potential energy has no real significance. It's really only the difference in potential energy that has physical meaning. Okay. So if we take this graph on the left, this graph on the left here is actually a graph for U equals G little m big M over R. Sorry, negative. Okay. This is a graph of the potential energy as you get further from the Earth's center. So for example, this is 1 times the radius of Earth. So this is at the very edge of Earth. What is your gravitational potential energy with respect to you and the Earth, right? And if we take that little segment, if we take this little segment right here and we blow it up here, right, you can see that segment is really linear. Notice what's happening here, okay? This graph is changing by 9.8, okay, as it goes. And you'll notice that what's happening is, this segment, this is a very, very small piece, by the way. Do you notice that in the grand scheme of things, 9.8 is really not that much here, right? This is, because we're talking about things that are in the 62 millions, okay? Um, okay, and then you'll notice that you're a distance. This is when you're on the ground at the very end of the radius of Earth. This is the radius of Earth plus 1, and it's not like plus 1 radius of the Earth. It's literally 1 the number. Okay, and you'll notice that this whole line is linear. You can find that the change in potential energy, right, is equal to m times g times the change in height, right? So this is kind of how we approximate the MGH on the ground of Earth, right? It's kind of weird, but that's how we get it. Okay, this just kind of makes things easier for us. It's not too huge of a deal, but that's just kind of where we get it from. This graph, by the way, is actually just a graph of U equals MGH. Okay. Okay. All right. Well, that is gravitational potential energy. All right. Have fun.